Hey everyone, welcome to Computer Science Made Easy. So today we're going to tackle one of the absolute biggest bottlenecks in modern AI. What really happens when you ask a language model to chew on millions of words all at once? Well, we're about to break down some pretty groundbreaking research that offers a really fascinating solution. Let's get into it. All right, so the paper we're diving into today comes from MIT's Computer Science and Artificial Intelligence Lab, CSAIL. It's by Alex L. Zhang, Tim Kraska, and Omar Khattab, and it's called Recursive Language Models. And listen, this isn't just some small tweak on existing models. Oh no, this thing completely rethinks how AIs should interact with just massive amounts of text. It's a total paradigm shift.
Okay, quick roadmap for today. First, we got to understand the problem, something called the context rot paradox. Then, we'll get into the new solution, this RLM paradigm, and peek under the hood at its RPL environment. After that, we'll check out the performance, see how it holds up under pressure, and finally, we'll wrap up by talking about what this all really means for AI. Let's do it.
So, first up, the context rot paradox. Yeah, it sounds a little intimidating, right? But really, it boils down to this super simple but really frustrating problem. For an AI, sometimes more information is actually a bad thing. Kind of counterintuitive, huh?
Think about it. You'd assume that just giving an LLM more data, more context, would naturally lead to better, smarter answers, right? But it's just not that simple. What actually happens is as you start force-feeding millions, and I mean millions, of words into a model's context window, its ability to find the needle in the haystack, the crucial details, and to reason effectively, well, it starts to go downhill, fast.
And this whole performance drop-off, it's a really well-documented thing called context rot. The best analogy I can think of is imagine trying to find one specific sentence in a giant library, but instead of using the card catalog, you have to read every single book from cover to cover. Eventually, you're just going to get completely lost in the noise. That's what's happening to the LLM. And wow, this graph from the paper really just lays it all out in stark numbers. Just look at the performance for a frontier model like GPT-5 on these really tough tasks. As the input length, that's the bottom axis, gets longer and longer, the performance, it just nosedives. It absolutely plummets. The model is literally getting lost. It just can't keep up with complex reasoning when it's drowning in that much data. This is context rot in action. Okay, so how do we fix this? The obvious answer might seem to be just build a bigger context window, right? Well, the researchers at MIT, they did something way smarter. They didn't just build a bigger box. They completely reimagined the whole interaction from the ground up. And here's the key insight, the big aha moment. The idea is to stop treating that massive prompt like a book that has to be read cover to cover. Instead, treat it like a database that can be queried. So the LLM shifts from being this passive reader to being an active investigator, digging for clues. Now, if you've been around computer science for a bit, this might sound familiar. The inspiration comes from a classic concept called out-of-core algorithms. Just think about a computer with, say, not a lot of RAM, trying to process a huge file. What does it do? It doesn't try to load the whole thing at once. It would crash. Instead, it cleverly fetches only the little chunks it needs from storage, piece by piece. It's a really brilliant analogy for what they're doing here. All right, so how do you actually turn this idea into a working system? Well, that brings us to the Recursive Language Model, or RLM for short. And this, my friends, is where the engineering gets really clever. So it all breaks down into this pretty slick 5-step process. This is what transforms the LLM from just a reader into an active programmer. So instead of just swallowing the whole text, it loads it up as a variable in a programming environment. Then it literally writes its own code to search and filter that variable. It breaks the big problem down, and then, and here's the magic, the recursive part, it calls up a submodel, a smaller version of itself, to tackle these little mini problems. Once those are solved, it stitches all the answers back together. So cool. This diagram here shows the RLM in its natural habitat, a Python REPL. And if you're not familiar, REPL just stands for Read Eval Print Loop. It's basically a live interactive coding sandbox. Now, you can see on the left, the main LLM isn't reading the text in the traditional sense. Nope, it's acting like a conductor of an orchestra. It writes Python code to strategically slice and dice that huge prompt into smaller, relevant pieces. Then, you can see the arrows, it calls on its submodels, these little copies of itself, to go analyze just those pieces. And then, of course, it pulls all the results back together at the end.
And what's crazy is that in practice, this leads to these fascinating emergent behaviors. The model with zero specific training for this just starts acting like a real programmer. You'll see it using regular expressions, regex, to hunt for keywords, or it'll even define its own Python functions to process data in batches, just to make its own recursive calls more efficient. It's literally problem solving on the fly. It's incredible. Okay, so the theory sounds really elegant, right? But the real question is, does it actually work? I mean, when the rubber meets the road on some incredibly difficult tasks, well, the researchers put it through the ringer with some truly massive benchmarks. And the results? Honestly, they're staggering. We're talking about RLMs successfully handling inputs of over 10 million tokens. Now, to put that into perspective for you, that's about the same amount of text as the entire Harry Potter series. It is orders of magnitude beyond what any standard model out there today can even dream of handling. And get this, take a look at this comparison on the Olong pairs benchmark. Now, this task is ridiculously complex. It involves comparing pairs of items across a massive dataset. The base GPT-5, it completely bombs, scores less than 0.1%. It's a total failure. But the RLM version, using that same base model, it pulls off an impressive 58% F1 score. That's the difference between an impossible task and a solvable one. And here's the kicker. You'd think this dramatic performance boost would come with a crazy high price tag, right? Well, incredibly, that's not necessarily the case. Because the model is so much smarter about what it chooses to process, the median API cost is often comparable to, or get this, even cheaper than just trying to brute force the whole prompt into the base model. It's not just more effective, it's actually more efficient. Wild. So, let's step back for a second. What's the big picture here? What's the major takeaway from all of this? Why should you care? Okay, the really key thing to understand is that RLM isn't just a bigger bucket for text. It's a fundamental shift in strategy. We're moving away from in-context learning and towards in-environment problem solving. It lets the model use tools, in this case, code, to actively dissect a problem instead of just passively trying to absorb all the data at once. And that's how it sidesteps context rot completely. Now, it's not perfect. There's a trade-off, of course. The paper is clear that because these subcalls happen one after another, it can be slower, but the potential to tackle problems that were flat out impossible before, it's just immense. So yeah, this research really does open up a whole new world of possibilities. And that's where we want to bring you into the conversation. So now it's your turn. We'd love to hear your thoughts down in the comments. What do you think are the biggest risks here? I mean, we're talking about a model that writes and executes its own code to figure things out. What happens when that code is buggy? Or what if it just completely misinterprets the task and goes off on some wild goose chase, burning through resources? Let us know what you think. And hey, on the flip side of that, let's talk about the good stuff. What are some of the most exciting new applications this could unlock? I mean, just imagine analyzing an entire corporate code base to find one tiny hidden vulnerability, or performing legal discovery across millions of documents, or maybe helping a scientist synthesize findings from literally an entire field of research. The possibilities seem kind of endless, right? All right, that's all we've got for this breakdown. Seriously, we can't wait to read your thoughts on the risks and the amazing potential applications down in the comments. Thanks so much for watching Computer Science Made Easy.